Welcome to Section 3, Lesson 1. Across Section 2, we learned how to manipulate algebraic expressions, combining like terms, distributing, simplifying nested parentheses, evaluating at specific inputs, translating English into algebra, and recognizing standard expression templates. Today, Section 3 opens with the next major step, solving equations rather than just simplifying expressions. A linear equation is the simplest possible form of equation in algebra, and almost every harder equation we will encounter for the rest of the course is solved by reducing it down to a linear form first. Mastering linear equations is therefore the gateway to almost every other solving technique in algebra, and the techniques we cover this week scale up directly into linear systems, polynomial equations, rational equations, and exponential equations later in the course. First idea on the board. A linear equation is one whose variable appears only to the first power with no exponents, no square roots, no variables in the denominator, and no products of variables with themselves. The standard form is a times x plus b equals c, where a b and c are specific numbers and x is the variable we want to solve for. The structure x plus b equals c has a single variable on one side, a constant offset, and a known number on the other side. Recognizing this structure on every equation tells you instantly that one step or two step inverse operation methods will solve it cleanly. Second idea. Solving an equation means finding the value or values of the variable that make both sides numerically equal. For a linear equation, there is always exactly one solution, exactly zero solutions, or infinitely many solutions, depending on the specific numbers in the equation. For most beginning examples, there is exactly one solution, and the solving procedure is a small handful of inverse operation steps that reduce the equation to the form x equals some specific number. The number on the right side, after the procedure finishes, is the unique solution. Third idea. The solving procedure rests on two principles. First, you can apply any operation to both sides of an equation without changing the solution, as long as you apply exactly the same operation to both sides. This is the balance principle, and it is the only thing that lets us manipulate equations safely. Second, every algebraic operation has an inverse. Addition is undone by subtraction, multiplication by division, squaring by square root, and so on. To isolate the variable, we apply the inverse of every operation that is hiding the variable, in reverse order from how the operations were applied. Together, the balance principle and the inverse operation principle cover the entire mechanics of equation solving across the rest of algebra and well into calculus and beyond. Today we apply these two principles to the simplest one-step linear cases. A linear equation is one in which the variable appears only to the first power with no exponents above 1, no roots, no variables in denominators, and no products of variables with themselves. The standard form is a times x plus b equals c, where a b and c are specific numbers. Recognizing this exact structure on any equation immediately tells you that the solving methods of Section 3 will work cleanly without any of the more advanced techniques from later sections. Here is the structural test. To check whether an equation is linear, scan the variable terms and confirm three things. First, no x squared, x cubed, or higher power of x. Second, no x in a denominator. Third, no x inside a square root or other root function. If all three checks pass, the equation is linear and the Section 3 techniques apply. If any check fails, the equation is non-linear and requires a different solving toolkit from later sections. Step 1 in the solving workflow. Identify which operation is currently being applied to the variable. In the equation x plus 7 equals 12, the operation hiding the x is the addition of 7. In the equation 3x equals 18, the operation hiding the x is multiplication by 3. The first move is always to name the operation being applied so you know which inverse to bring in. Step 2. Apply the inverse operation to both sides of the equation. Addition is undone by subtraction, so to undo plus 7, we subtract 7 from both sides. Multiplication is undone by division, so to undo times 3, we divide both sides by 3. The balance principle guarantees that doing the same thing to both sides leaves the solution unchanged. After the inverse step, the variable is alone on one side and a specific number is alone on the other. Step 3. Read off the solution. The form x equals some specific number is the goal of every linear equation solving procedure. Once you reach that form, the number on the right side is the unique solution to the equation. As a verification step, you should always substitute the solution back into the original equation and check that both sides really do equal the same number. The substitution check uses the evaluation skill from section 2 and catches almost every solving error in 5 seconds. Today we walk through 2 one-step solves to build the workflow, and the next several lessons extend the same workflow to 2-step, multi-step, and variables on both sides equations. Here is the first worked example. Solve the linear equation x plus 7 equals 12. The variable x is hidden behind a single addition operation, and the equation is therefore a one-step solve using subtraction as the inverse operation. The structure is the simplest possible form of linear equation, and it makes a clean introduction to the solving workflow. Step 1. Identify the operation currently applied to x. The expression x plus 7 contains addition 7 is being added to x. The inverse operation that will undo the addition is subtraction. To isolate x, we will subtract 7, but we must do it on both sides of the equation simultaneously to preserve the balance. Step 2. Apply the inverse to both sides. Subtract 7 from the left side and from the right side. The left side becomes x plus 7 minus 7, which simplifies to x because the plus 7 and minus 7 cancel. The right side becomes 12 minus 7, which equals 5. The equation has now been transformed into x equals 5. Step 3. Read off the solution. The equation x equals 5 is in the goal form variable on one side, specific number on the other side. The solution is x equals 5, the unique number that makes the original equation true. Step 4. Verify by substitution. Plug x equals 5 back into the original equation. 5 plus 7 equals 12. Both sides do equal 12, so the solution is verified. The verification step is fast and catches almost every solving error, so always include it. So the solution is x equals 5. The big lesson from this example is the entire solving workflow in microcosm. Identify the operation hiding the variable, apply the inverse to both sides, read off the solution, verify by substitution. Every linear equation we solve for the rest of the section follows exactly this rhythm, with extra steps added when the operations stack into 2 or 3 layers. The one-step case is the foundation, and getting it absolutely solid now means the multi-step cases later this week will feel like extensions of an already known pattern rather than new procedures. Here is the second worked example. Solve the linear equation 3x equals 18. The variable x is hidden behind a single multiplication operation, and the equation is therefore a one-step solve using division as the inverse operation. Same workflow as the previous example with a different inverse operation. Step 1. Identify the operation currently applied to x. The expression 3x is shorthand for 3 times the x is being multiplied by 3. The inverse operation that will undo the multiplication is division. To isolate x, we will divide by 3, but we must do it on both sides of the equation simultaneously to preserve the balance principle. Step 2. Apply the inverse to both sides. Divide the left side by 3 and the right side by 3. The left side becomes 3x divided by 3, which simplifies to x because the 3 in the numerator cancels with the 3 in the denominator. The right side becomes 18 divided by 3, which equals 6. The equation has now been transformed into x equals 6. Step 3. Read off the solution. The equation x equals 6 is in the goal form. The solution is x equals 6, the unique number that makes the original equation true. Step 4. Verify by substitution. Plug x equals 6 back into the original equation. 3 times 6 equals 18. Both sides do equal 18, so the solution is verified. So the solution is x equals 6. The big lesson from this example is the same workflow as the previous example with a different inverse operation. Multiplication on the variable side gets undone by division on both sides. The pattern is universal, every operation has its inverse, and applying the inverse to both sides isolates the variable cleanly. Tomorrow we extend the workflow to equations where two operations stack on top of the variable, and we apply the inverses in the correct order using a small priority rule that mirrors PEMDAS. The two-step extension is straightforward once today's one-step pattern is solid, and by the end of the week you will be able to solve any linear equation in any of the standard forms with the same disciplined inverse operation procedure that we previewed in these two examples. 3 mistakes that catch every algebra student during their first week of solving linear equations. Each one is fixable with a small explicit habit applied on every equation. First mistake, applying the inverse operation to one side of the equation only and not the other. A student sees x plus 7 equals 12 and subtracts 7 from the left side to get x equals 12, forgetting to also subtract 7 from the right side. The equation no longer balances and the resulting answer is wrong. The fix is to make the both sides language explicit in your written work. Write -7 below both sides of the equation, or write the operation in the margin with arrows pointing to both sides. Visually committing to the balance principle prevents the one-side error. Second mistake, applying the wrong inverse operation. A student sees 3x equals 18 and tries to subtract 3 to undo the multiplication, getting an answer like x equals 15, which is wrong. Multiplication is undone by division, not by subtraction. The inverse operation pairs are addition undoes subtraction and vice versa. Multiplication undoes division and vice versa. Exponentiation undoes by root and vice versa. Memorize the 4 pairs and pause to confirm the inverse before applying it. Third mistake, dropping a sign or losing a number during the arithmetic step. A student sees -5 equals 10, correctly identifies addition as the inverse, adds 5 to both sides, but writes x equals 5 on the right side instead of x equals 15. Arithmetic mistakes during the inverse step are common because students rush. The fix is to write the arithmetic on the right side explicitly, 10 plus 5 equals 15, then x equals 15. Slow down on the right side and the sign drop errors disappear. Linear equation solving is the most used operation in all of applied mathematics and engineering. Almost every formula in physics, finance, engineering, and computer science is a linear or near-linear equation that someone must eventually solve for one of its unknowns at concrete numerical inputs. 4 broad sectors below. In physics, the kinematic equation final velocity equals initial velocity plus acceleration times time is a linear equation in any one of its 4 variables. Given the other 3, you solve for the 4th using exactly the inverse operation pattern we covered today, sometimes with 2 or 3 steps when multiple operations stack on the variable. The solving step happens in every physics calculation, and getting it reliably correct is one of the highest leverage skills you can build for the entire physics sequence. In personal finance and accounting, the simple interest equation final amount equals principal plus interest is a linear equation in either the principal or the interest given the other and the final amount. Loan payments, savings projections, and tax calculations all depend on solving similar linear equations for one unknown given the others. The bookkeeping work that anyone running a small business does daily is essentially continuous linear equation solving in disguise. In electrical engineering, Ohm's law voltage equals current times resistance is a linear equation in any one of its 3 variables. Given any 2, you solve for the 3rd with one-step division or multiplication, exactly the workflow we covered today in example 2. Every electrical engineer doing circuit analysis solves Ohm's law and its many cousins all day long, and the algebra they use is precisely the one-step and two-step linear equation algebra of section 3. In software engineering, the runtime of a loop or the iteration count to reach a target is often modeled as a linear equation in the loop count. Given a base setup time, a per iteration cost, and a target total time, solving for the iteration count is a one-step or two-step linear solve. Algorithm analysis, capacity planning, and performance budgeting all rely on this kind of solving constantly. The skills you are building this week are the workhorse skills of applied computing across every kind of system. 3 things to take with you from this lesson today. Linear equation solving is the foundation of every later equation solving technique in algebra and the most used solving skill in all of applied mathematics and engineering across the entire economy. First, a linear equation has the structural form a times x plus b equals c, where a b and c are specific numbers and x is the variable. The defining structural feature is that x appears only to the first power, no exponents above 1, no roots, no x in a denominator, no x times x products. Recognizing the linear structure on any equation tells you immediately that the inverse operation methods of section 3 will solve it cleanly without needing the more advanced techniques from later sections of the course. Second, solving means applying the inverse of the operation hiding the variable, applied identically to both sides of the equation. The both sides discipline is the balance principle and is what guarantees the solution stays the same. The inverse operation pairs are addition undos subtraction, multiplication undos division, exponentiation undos by root taking. Memorize the 4 pairs and apply them consciously rather than reflexively until the workflow becomes automatic over the next few lessons. Third, always verify your solution by substituting it back into the original equation and checking that both sides really do equal the same number. The verification step uses the evaluation skill from section 2, takes about 5 seconds, and catches almost every solving error before it becomes a wrong final answer. Build verification into your standard solving rhythm as a permanent, non-negotiable final step. Coming up next, the lesson called two-step equations, where the variable is hidden behind 2 stacked operations, and the inverse procedure requires applying 2 inverses in the correct order. The 2-step extension is the natural completion of today's one-step workflow and is the form of linear equation you will see most often in homework and on tests.